David,
Yes, ma'am.
by the way, I'm sorry about Stone.
Oh, well, thank you. It's let's look on the positive side. It was a good learning experience, and we had a team of people who worked very well together. I really have no complaints. Everyone did their best. I hope people feel I did my best, and I thought for a very stressful activity, it was one in people remained positive and worked as hard as they could and did good things. And the ideas and the information we learned were all captured and will perhaps be available to some more early career person to carry those ideas forward in the future.
Don't forget, you guys are on YouTube.
Oops.
No, I'm not forgetting, because those are all positive statements.
So
I
it's
just wanted to
recording.
remind you.
Wait. Is it recording now?
Yeah.
Mhm.
Oh, it's not
Yes.
1 o'clock yet.
No,
But no, not trouble.
Hello.
I have to make it go live.
Marcos is here. Marcos is here. Can Marcos be in charge?
Yep.
Okay.
Dave,
Yeah.
you'll have to make him co-host or host.
How do I do that?
Go to his name in chat.
All right. Okay, I found chat. I don't, yeah.
Or I think it's in participants, actually.
Yeah.
Yeah, and then if you go by his name, click on more, and then you can make him host or co-host.
Yes, I can do that. I'm going to Marcos Moore, make host.
Or co-host.
You are now host.
Okay, thank you.
All
Just
right.
a question. Can you hear? There's a background noise here. One of my neighbors is doing some construction.
No, we don't hear it.
Okay, good.
All right, thanks everyone. We'll see you later.
Bye, Kyle.
If someone texts me, I'll try and watch YouTube, but I'll try and turn it off when everything's done. Or if Jason or Marcos could do that, that would be helpful.
I can stop the recording here. I can start the recording here. That's
No,
right.
and just ending the stream on YouTube.
Oh, sure. Yeah, I can log into YouTube and keep an eye on that.
Okay,
Okay,
excellent.
that's
Thanks,
great.
guys.
Sounds good.
Great. Bye.
Bye.
Bye-bye.
Bye. Bye, guys.
So
Mei-ching,
will
I sent
start
the- I was going to say I sent the link to our 673 group as well, so hopefully people will join. So. Oh yeah, what was that, Marcos?
I'm gonna wait another 2 minutes to start.
Okay, sounds good.
We can let everyone in, right? Oh, yeah, guys are using this.
Yep, might as well let him in.
Okay. Okay, it's 3 minutes past noon in Washington, DC. We can start. Hello, everyone. This is Marcos. Welcome to the Magnetosphere seminar series. Before we start, I'd like to remind you that this presentation is being recorded. So please keep your microphone on mute and send your questions in the chat box. I will read them at the end of the presentation. Today, we are delighted to have Dr. Mei-ching discussing an overview of the inner magnetosphere modeling and new developments in CIMI. Dr. Mei-ching works at the Geospace Physics Laboratory at NASA Goddard Space Flight Center since 2001. Dr. Falk received her bachelor in physics in a diploma in education from the Chinese University of Hong Kong, a master's degree in physics from the Eastern Michigan University, and the PhD in atmospheric and space sciences from the University of Michigan. Dr. Falk's main research interests are studies of the radiation belts and ring current during geomagnetic active periods, understanding the mechanisms responsible for their intensification and decay by numerical modeling and data analysis. She has developed a complex model named as the Comprehensive Inner Magnetosphere Ionosphere Model, CIMI, that can compute and predict the energetic plasma fluxes in radiation belts and ring current region. Dr. Falk was a participating scientist of the IMAGE mission and is the project scientist of the TWINS mission. She is heavily involved in neutral atom imaging. The modeling tools that she developed have contributed greatly in interpreting images from the neutral atom imagers on IMAGE and TWINS. Also, Dr. Falk was involved in the Van Allen probes mission. The CIMI model was able to run in real time to predict energetic ion and electron fluxes that Van Allen probes satellites observed. Thank you, Dr. Mei-ching, for accepting our invitation, and please go ahead.
Yeah, thank you for the invitation. Yeah, so now I should share my screen, right?
Yes.
Okay, so you see my screen, okay?
Yes, perfect.
Okay, anyway, so yeah, today I'd like to talk about an overview, hopefully it's a good overview of the inner magnetosphere modeling. And at the end, I'd like to focus on the CIMI model. So I'd like to acknowledge my colleagues for their contribution and constant support and their friendship in my career. So you can see my cursor, right?
Yes, we can.
Okay, good. Whoops, wait a sec. Oh, okay, so at the beginning, I'd like to have a very brief overview or introduction of the three major plasma population in the magnetosphere: the radiation belt, the ring current, and the plasmasphere. So, and they are co-located. So we usually differentiate them by their energy range. So for radiation belt, I mean, maybe around 500 is the kind of the transition from ring current to radiation belt. And the plasmasphere is the cold plasma and have the temperature just a few EV. Oops, sorry. So we are interested in this plasma population because they have not only they have a very interesting scientific significance, but also they have ample space weather application. So I just list some the space weather relevance here for internal charging, surface charging, and charge utilization from radiation bellwether current and plasmasphere. So many models has been developed to study the inner magnetosphere and the plasma's population inside. So I think need not to say, a simulation model is very important. We can use them to understand the physics behind the observed phenomena. And also simulation model provide very important method of analysis, and which is easy to verify, communicate, and understood. And most importantly, simulation can be used to predict certain phenomena. Okay, before I continue, I just want to make sure you can see my my title here fine, because on my screen I saw something blocking my title, but for you guys, okay?
Yes, we can see Rice convection model by RCM.
Oh, okay, good. I just want to make sure. Okay, sorry. Okay, let me continue. Yeah, so the Rice convection model, I can say is pioneer model of the magnetosphere inner ionosphere coupling. So this is the logic diagram of the Rice convection model RCM from a very old paper in 1981, and this is the, okay, let us start with the hot particle distribution in the magnetosphere, and the gradient and curvature drift current produce the perpendicular current, and from the conservation of current or current continuity, we can calculate the field line current. And the same way for divergent J0, we have the you can say we can have the ionospheric current, and with the ionosphere conductance, we can solve the potential in the ionosphere, and then we map the potential along the field line, and we have the electric field in the magnetosphere, and then again use this electric field, and we can advance the plasma in the magnetosphere, and then complete this logic cycle. So this is a very famous, we call resonance cycle, and it's the foundation of the RCM model, and this is a more modern version of the RCM model. Also, we can look at this logic diagram from starting from the plasma density in the magnetosphere. So this, the upper block is magnetosphere, and the lower block is the ionosphere. And the connection between the magnetosphere and the ionosphere is the magnetic field. So the magnetic field connect these two important regions. And the computed quantities from RCM is all these rectangle, and the model output is the oval here. So, many people know about RCM. That has been around for a few decades now. So I want to highlight, from the paper from Frank DeFalco for some very interesting feature that predicted by RCM is often observed from satellite. For this, and then because of RCM, there are many important terminology or we have using when we talk about the electric field in the magnetosphere, like shielding, or undershooting, or penetration, and overshooting. So this is the okay, on all this plot, the sun is on the left, and this is the equipotential, and for the potential, positive potential is in solid curve, and negative potential is in dash lines. So you see when we talk about shielding, what we mean is the electric field generated by the wind current will shield the innermost of the magnetosphere from the cross-tail electric field. So you see the electric field in the inner part is weaker. And for undershielding, or in other words, penetration, that happens when shielding is disrupted by increase of the cross-tail electric field. So you can see the electric field in the inner part is still pretty very strong. And in some cases, when wind current electric field established and it's even stronger than the cross electric field when the cross electric field is suddenly decreased. So in that case, you will have the situation about overshooting. When overshooting occurs in the inner part of the magnetosphere, the electric field direction is not done thus, but instead but will be thus done the reverse the direction. And in this situation, we call it overshooting. And another feature that we often seen from observation also can be explained by the RCM simulation is SAD or SAPS. So that is a fast westward flow in this the midnight sector that caused by the very strong field line current or ionospheric current flowing in a low conductance region. In this region, because it's on the night side, so the conductance sometimes is low in this. And also this is a subaurora region, so the conductance or precipitation is low. And then you have strong current and below conductance, it will produce a very strong electric field. So this is the SAPS and SATS region. Another feature from this plot is the eastward skewing of the convection potential in this in the midnight dawn sector, caused by shooting and also a shock gradient of the ionospheric conductance in this dawn terminator. So just keep this in mind, and this is pretty well known and also often observed. And RCM have recently, not recently, but I think have maybe two decades ago, anyway, have extended to with force balance component. So this is make sure the J cos B is equal to gradient P, and they have a friction code coupled with the RCM to make sure the force balance condition. So this is some run result from the RCM-E, the RCM wise convection model equilibrium, and from Yang et al. And also they run test particle on the RCM-E field, and to look at how particle access from the near Earth plasma sheet to the trap region. And they identify particle called bubble particle or long bubble particle and trapped particle from different color. So bubble particle is the black particle, and long bubble particle is the red dots, and the trap particle is the magenta particle. And they identify that if the particle they're from a region of low PV gamma, that they identify that as a bubble particle. If particle is not from the low PV gamma region, that is the long bubble, and particle can stably trapped in the near region is trapped particle. But anyway, from this, okay, this is running. I think running from for a storm at 4 different times, and again, sun is on the left, and the arrow, the blue arrow here, represent the bubble injection, and where you see a large number of bubble particle coming in from the from the plasma sheet. So, and the conclusion of this study is the simulation suggests that the bubble will contribute over 50% of the wind current energy during moderate and intense storms. So without CME, we confirm, or we suggest that the bubble of the fast flow bursty bubble is very important for wind current buildup. Okay, now we move on another model, the comprehensive wind current models, CLCM. And CLCM is the wind current model and with the RCM MI coupling component. And this work was initiated by Professor Dick Wolf in 2001, and this is a paper from 2001. So I would like to highlight the main difference between RCM and CLCM. And for RCM, there's a RCM because RCM assume isotropic pitch angle distribution. So there's only one variant, is the energy variant defined by lambda x here. This is the W is the kinetic energy, and V is the flux to volume per magnetic flux. But CLCM consider full pitch angle distribution. So the debate invariant is M and K is the magnetic moment, and the longitudinal invariant defined K defined by the combination of the first and the second debate invariant. So this is the main difference between RCM and CLCM. And CRCM. I like to highlight some significant contribution from CLCM, and one of the example is CLCM produced help to interpret the ENA image taken from the image mission here. This is an example for the storm in August 12, 2000, and this is the 2 times on that day, 8 UT and 11 UT for 2 energies. This is 27 to 39 keV, and this is high energy 50 to 60. And the local time is labeled here. So this is midnight here. Anyway, so this is ENA image give us the global view of the wind current distribution, especially in local time. So for this, during the main phase of the storm or near the or early recovery of the storm, you see for these 2 energies, the peak of the wind current happened in the post-midnight sector from like here and here. And this is, when we first saw this, is kind of contradict with conventional belief that we thought wind currents to be the peak is around dusk or in the midnight dusk sector, but the image indicate that is no, it is in the post-midnight sector. So we ran a simulation to see how we can understand this local time distribution. And the first run we did is just use the Weimar, the empirical Weimar electric field. And then the second one is using the MI coupling CLCM electric field. So this column is the flux. Okay, we only focus on the 27 to 30 keV ion, and this is the at 8 UT, and this is at 11 UT. So when we use Weimar, we did see the peak of the wind current is in the dusk midnight sector, and then but we use from IMA and the from CLCM, and we see what they have very different potential pattern. From IMA, you see very strong electric field in the dust midnight sector, and the electric field at dawn is pretty weak, but for CLCM also you see strong electric field in the dust midnight sector, but you also see a very strong electric field and also a eastward skewing electric field that near dawn, and that formed and that gives the strong particle, the ion flux for the wind current, and also that produce the ENA, the peak of the ENA of flux that we saw from the image or from the simulation. So the conclusion is the eastward skewing of the potential caused the post-midnight peak of the ENA that consistent with the image observation. So once again, the MI coupling of the electric MI coupling is very important to understand the electric field pattern, the electric field distribution, and also particle dynamics or distribution in the inner magnetosphere. So, okay, so now I move on, also talk about some extension or improvement of the CLCM, and in the past, I mean, maybe around 10 years, CLCM combined with a radiation belt environment model, and then we name it as CIMI, Comprehensive Inner Magnetosphere Ionosphere Model. So because with the radiation belt component, we have, of course, the wave particle interaction or wave diffusion is very important for radiation belt particles. So now CIMI is like a type of convection and diffusion model, and the particle motion in the configuration space is solving by this convection equation, and in this way we can have the local time distribution as well. But for the particle, for the distribution function, the change of distribution function in the velocity space, we have the using the diffusion approach. So all this is the okay. In addition to this Convection diffusion equation, we also have a co-plasma component that we solve the fluxed content of the plasmasphere, and of course CIMI and like CLCM have the MI coupling component solving the convection potential by the fuel line current produced by the wind current gradient, pressure gradient. Anyway, this is all the output from CIMI, and not only in the magnetosphere but in the ionosphere. We also CIMI produce the particle precipitation, and also CIMI consider the energy transfer between the wind current and the plasma, and also CIMI calculate the heat flux to the plasma sphere. That this is an example is the heat flux. See that from the ionosphere. Okay, so now I move on. Another model is the RAM model, the wind current atmosphere interaction model. The RAM model, again, I just highlight or the main difference between RAM and CLCM is CLCM follow the debit invariant M and K, and because they are invariant, so in the CLCM or CIMI model, there's no the MDK term. RAM follow the particle energy and the pitch angle or cosine pitch angle mu, and because they are not invariant, so there's a let me see. Yeah, there's the DE term and also d mu dt term in the convection equation. So, but the advantage of using the E and mu as parameter is then is more convenient to use this coordinate system to calculate wave diffusion, because most of the wave diffusion model provide the diffusion coefficient in terms of pitch angle and energy. So when RAM solve this convection diffusion equation, they don't have to map the phase space distribution from one coordinate to another coordinates. So this is the main advantage. Okay, another main difference between CLC and RAM I didn't say here is the spatial grid. CLCM, the spatial grid, like RCM, is in the ionosphere, and the RAM model, the spatial grid is at the equator. Okay, so some important finding from RAM. This is an example published by Jordan Nowak 2008. As I said, the RAM model was designed to look at wave particle interaction, and this is the simulation during a storm. And here show the EMIC wave gain and amplitude at this 3 times during the storm. And you see, this is the EMIC gain and the corresponding wave amplitude. And this is also RAM have a Plasmasphere model inside it. And so this is the predicted Plasmasphere density. And with this calculated EMIC amplitude, and RAM calculated precipitation, electron precipitation here, and ion precipitation. So you can see the strong precipitation happen at the, like here, oops, sorry. Here is near the plume area, and also strong precipitation also seen in the on the day side here. Okay. Again, RAM also was extended and improved by adding a force balance component in it. And the new model is called RAM FCB, RAM with self-consistent B. And this showed the calculation comparing I think it's dipole magnetic field with the self-consistent B, and at the peak of the storm of this on April 22, 2001, and this showing, I think this plus showing different energy and the flux of different energies. So the conclusion of this study is we find the weaker fluxes with self-consistent B. With the self-consistent B, the flux or the pressure or the wind current is lower. And this is a kind of like a self-modulation if we consider things more self-consistently. Okay, next I move to the development of the inner magnetosphere. When we like to, okay, I have been focusing on the coupling between the ionosphere, the magnetosphere and ionosphere. But of course, we are also interested in the coupling of the magnetosphere with the solar wind. In order to do that, we need to couple the inner magnetosphere model with the global MHD model. That's what I meant by when I am Miss GM. So the first work of this kind is the coupling between the RCM model with the Bessarus MHD model. So this is a paper by Darren, 2004, showing the coupling between RCM and Bessarus. And okay, so the coupling mainly is the particle pressure from, or the particle pressure from the hot ring current will input to the Bessarus model. So mainly is to map the RCM superthermal pressure to the Bessarus grid. And of course, because RCM, so assuming the pressure is constant along the field line. So this is what RCM input to Bessarus, and in turn, Bessarus provide the particle mass density and okay, let me see, yeah, and also the flow velocity to the RCM, and also the I mean, this mainly for providing RCM the boundary condition, but also Bessarus provide the global magnetic field and electric field to the RCM that will be are used for RCM to move particle around to calculate the electric drift and the magnetic drift. So this is a very successful, also a pioneer work, and this is some initial result for that study, and comparing the particle pressure in the inner magnetosphere with the coupling and without the coupling. So without the coupling, the MHD pressure is very low, but with the RCM coupling, you can see very high pressure, and also that is consistent with the observations in the inner magnetosphere. On the other hand, the mass loading or the coupling with the RCM will reduce the cross-polar cap potential. So this is the cross-polar cap potential calculated by Bessarus with RCM and without RCM. Note that the scale not the same, but you can see the potential, the cross-polar cap potential with RCM is lower than the run with Bessarus no RCM coupling. So after this work, now we have many projects, many coupling work are going on, and not only Bessarus, but MHD model like LFM, Gamma, OpenGGCM also coupled with inner magnetosphere model like RCM, CIMI or CRCM, and RAM FCB has been coupled with a global MHD model, and some of the model, the couple model, is in operation to provide real-time space weather prediction. Okay, another topic I wanted to mention is another new development in the inner magnetosphere modeling is the data assimilation. So some models start to include data assimilation in their modeling. So I give here is a few examples. Is the work 3D model have the we construct the relativistic electron using gamma filter, and also Jacob Bollet have a project that using neural network to produce a 3D dynamic electron density model. It's the Plasmasphere model, and I know they are also now working on machine learning to predict the radiation belt or energetic particle distribution as well. And another effort was led by Wanya Jordanova, the SHIELD project that I will talk about now. The SHIELD project is the space hazards induced near by large dynamic storms, and the main assimilation model is the RAM-FCB and BESRS, and there's other component. There's a ionosphere dynamic component, and also some PIC, CD, and 3Ds and particle tracing. So the special or the new component is the data assimilation model, and that was used to reconstruct the radiation belt flux that in the magnetosphere. So here is an example, and see what the data assimilation will affect the prediction. So here show a prediction during, let me see, I forgot, but anyway, during a storm. And so at 3 different energies, so 62 here, 97 and 133 keV during a few orbit of the RBSP satellites. So look, they use they assimilate the RBSP-A data into the RAM-FCB and then validate it with RBSP-B. So so we look at the observed RBSP-B flux is the green curve. This is the observed, the green. And then if they just run the RAM model without data assimilation, they have the red curve. But if they add the assimilation, the assimilated data from the RBSP-A data, so you see the agreement is greatly improved here. So that show the data assimilation is very important to give us better prediction of the radiation belt. Okay, so now, in the last 10 minutes, I'd like to talk about some new development in the CIMI model. The first development I'd like to talk about is the coupling with the BESRS, and there's some new stuff there. And this is from a paper from Alex Grosser. And in this, in the new coupling, we separate, we add a separate plasmasphere fluid into the MHD equation. And also we include the hemispheric asymmetry in the outflow. And also we separate the solar wind and ionosphere H+. So we have two H+ fluid. One, they originate from the solar wind, and one is from the ionosphere. But I will more focus on this development is a separate plasmasphere fluid. So here show the calculated plasmasphere density, and from this is a top view, and this is the side view. And then you see the day side plume here, and you see the day side plume from the side, and the dot here is the separator. And as you see the dense plasmasphere or the plume will we see that in the reconnection region, and this mass loading may have effect on the local or global effect on the reconnection. So we find that really the effect is not only localized, but also have a global effect. So here I show the cross-polar cap potential drop as a function of time, and without the plasmasphere fluid, and the orange curve is with the plasmasphere fluid. You can see with the plasmasphere fluid, the potential drop is low, significantly lower than the run without plasmasphere. So we see that it's very important to include the plasmasphere fluid and to see the overall effect on the magnetosphere, on the reconnection, or on the global dynamics. Okay, another development I like to talk about is currently we have implemented IGF as internal fuel in CIMI. So with the IGF, what happened is because IGF, there's a north-south asymmetry in the IGF. So when we calculate the loss cone, this is what usually we use to calculate the loss cone is the magnetic field, the ratio of the magnetic field at the equator and the magnetic field at the ionosphere. But since the magnetic field in the ionosphere at north and south, they are not the same. So we will have different loss cone size on the at north and south. So that's what we always observe. Actually, the precipitation, particle precipitation at north and south, actually they are not the same. But we usually ignore this and then just assume north-south symmetry. That is not very good. So that's why we try to use IGF, a more realistic magnetic field, and to see to calculate particle precipitation. So when we talk about the IGF and north-south asymmetry, we have to organize our coordinate or our precipitation, not in terms of local time, but also in terms of magnetic longitude. So this is the magnetic longitude. But of course, okay, anyway, this is, and the color here is what we call is the loss cone asymmetry. This is how we define the loss cone asymmetry. So it's kind of like look at the comparing the loss cone size from northern hemisphere and southern hemisphere. So if you look at this definition, if you have the north cone size at north is bigger, then you have the A index is larger than 1. Is in this longitude range, the A index is larger than 1. And on the other hand, if you have the loss cone at south is bigger, then you have the A index is negative. So it's in this area, this big is a larger longitude area that the loss cone in south is bigger. And here, and when it is bigger at south, that means we predict or we should expect stronger precipitation in southern hemisphere. So this helps us to identify where you should have stronger precipitation at south and where you have stronger precipitation at north. And we do the calculation and look at the electron precipitation, mostly from the diffusion by Chorus wave. And also I organize this plot in terms of magnetic longitude. But at a particular time, the cross here is the direction of the sun. So you have the local time here is at noon. And this precipitation is calculated during the storm on March 17, 18, 2015 at these 2 times. So you look at, okay, this is precipitation at north and precipitation at south. And so it's very obvious that you see the asymmetry between north and south. So at this particular time or particular magnetic longitude, you see stronger precipitation in the southern hemisphere. But in this particular time, you see stronger precipitation in the northern hemisphere. So when we compare this with with the loss cone asymmetry, we did see that the stronger precipitation at north is in the region that the A index is larger than 1, and stronger precipitation at south is in the longitude range that the A index is negative. That's consistent with the prediction. Yeah, you have bigger loss cone here, then you have stronger precipitation here compared with at the northern hemisphere. So of course, this asymmetry in precipitation that will affect the ionosphere, the precipitation will cause a lot of dynamics in the ionosphere. So this work is possibly supported by a project called CUSIA, the Center of Unified Study of Interhemispheric Asymmetry. Is a joint center. So that's joint center study the interhemispheric asymmetry. So next, we look at whether this is consistent with the oscillation. Here, I show the 1-year average of these neutron precipitation by poles, by the lower poles, and also organize the precipitation in magnetic longitude. This is done by Christian Folati. And we look at we can also find the north-south asymmetry. This is north and this is south, and very interesting. We also see the asymmetry. Okay, look at the northern hemisphere. You see the stronger precipitation compared with the south in this longitude range are consistent with the A index is positive. And also, on the other hand, you see the stronger precipitation at south in this longitude range, also consistent with the negative asymmetry. Yeah. So what we predict is also consistent from observation. Okay, the last thing I'd like to talk about is the work about the interaction between the wind current and the plasmasphere by Coulomb collision. The energy transfer will flow into the south and northern ionosphere, and this work has been done a long time ago, and also the energy input is believed to be the energy power the SARA emission. It's a paper from Jenica Sira. And if we have a north-south asymmetry, maybe the heat flux also you will see is different between north and south. So in CIMI, we have calculated the energy or momentum change due to Coulomb collision, and we calculate the heat flux to the plasmasphere. In this plot is the warm heating at the equator. The sun is on the left, and you see this strong warm heat flux here, and then that very close near dawn, and then extended to higher L in the plasmasphere plume area. So when we integrate this warm heating and then look at the heat flux to the northern and southern hemisphere, you see they have different pattern. So even also the sun is on the left, and I label the magnetic longitude in this time is in this direction. This is north and south. So even we assume equal amount of heat flux flowing down to the north and southern ionosphere, but because of the footprint at north and the south, they are not at the same same location. So that's why you see the pattern, they're not the same. In addition to that, because the Fock strip volume at north and south are not the same. So this is the heating per unit area. So that will give you the heating per unit area, not the same, because the Fock strip, the cross section of the Fock strip is not the same at north and the south. So again, this kind of heating, many ionosphere, thermosphere model, they require heat flux from the magnetosphere. So I believe that the CIMI model and will provide them a more realistic magnetospheric heat flux to their models. And not only that, and we can also provide the NorthSouth asymmetry in that kind of heating. So I like to conclude, and so we have developed a magnetosphere model that consider cross-region and cross-energy coupling, and we identify the important processes like the wind current shielding, MI coupling, bubble injection, and also wave particle interaction, especially for radiation belt. And the inner magnetosphere model has been coupled with global MHD model, so enabling solar wind, magnetosphere, ionosphere coupling. And some recent and future effort data is assimilation and have additional separate plasmasphere fluid in MHD models, and also the interhemispheric asymmetry is also very important as well. And also something that we should do more in the future. Thank you.
Thank you, Mei-ching. That was very interesting talk. Thank you very much. Before I read the questions, I'd like to inform that there will be no seminar on Monday, February 21st, the next Monday. So we will inform you when the date of the next seminar. Our first question is from Charles. I believe it was around the slide 30. And he asked, how do these different models take in account the large outflow of the ionospheric plasma from the polar wind and polar cusp, which is energized to become the plasma sheet, ring current, and warm plasma cloak?
So okay, it's not a specific slide you're talking about.
Yeah.
Okay, okay. So you say how we distinguish the different outflow and populate the plasma sheet and the inner magnetosphere or the ring current. Is it the question?
Mm-hmm.
Mei-ching,
Yeah.
this is Rick Chappell. I know you've done a lot of work on the relative contribution of the ionosphere and solar wind to the magnetosphere, particularly with ion trajectories. So you're very familiar with all of that. And in looking at the models here, I didn't ever hear the polar wind mentioned, and maybe implicitly the polar cusp was mentioned as a source. But of course, Alex has recently included a polar wind, and when he runs that in at least specific storm cases, he finds that the H plus in the magnetosphere is dominantly from the polar wind and not from the solar wind.
Yes.
So I wondered about, in the models you've shown us so far, I didn't hear anything mentioned about the polar wind or the polar cusp source.
Yes, you're right. So that's what I meant here. Alex separate the H plus from the solar wind and the ionosphere. That will, as you said, that will better access to the solar wind source and the ionospheric source. I know I didn't mention about that in this talk, but because it's not the focus for this talk. But yeah, this is very important, and especially for this paper, Alex showed the the main contribution for the ring current is from the ionosphere, even for the H plus, because people always think about the hydrogen H pluses from mainly from the solar wind, but it's not. It's from the ionosphere.
Yeah, exactly.
Yeah.
That was a real surprise, I think.
Yes.
People had thought of certainly of O plus getting into the ring current, which it does, but the ionospheric H plus from the polar wind that started polar caps and went through the lobes was a new model result from Alex.
Yeah, I think to respond to the question, yes, we separate them. We very carefully look at the contribution from the solar wind and the ionosphere and the relative importance of the two sources to the plasma sheet and the wind current.
And there is a polar wind model in your model? Not plasmasphere, but is there a polar wind outflow model as part of this?
Yeah, when we coupling with like this figure, we're coupling with the yeah, we have see the coupling with the prom and also Bessara, and yeah, we have that.
Okay.
We take into account of it.
Thank you.
Okay, thank you, Mei-ching. This also answered, I believe this also answered the question from Ramia. She's also asking the same similar question. So I will skip that and go to the next from Jonathan. CIMI plasma sphere can be represented with zero energy channel or using the DGCPM. When you charge from zero energy to DGCPM, did the mass loading reconnection effects change?
Yeah, you're right. So this model is we use the dynamic core plasmasphere model? Yeah, the DGCM. Anyway, so we assume the temperature is just not zero, but one EV. That won't give you not the pressure, not much pressure, but this provide strong density feedback to the MHD model. Yeah, it's very cold. The pressure feedback is not that much. It's not important, but the density, even the density, the mass loading have a very strong effect, as I shown here.
Mei-ching.
Yes,
Jonathan. Very nice talk. My question was, back when you were using the zero energy channel to represent the plasmasphere, did you see this mass loading effect? Like did that thing produce a plume that went out to the? I don't have a good handle on what the plasmasphere was like when you were using the zero energy channel for the plasmasphere.
I don't say that as a zero channel. I just have a separate equation, but you can say zero channel. But anyway, okay. It's not the matter of when we use zero energy, but it's matter of whether we take the plasma sphere into and treat it as a separate fluid. Oops, what I'm going to. Okay, so what is new is not how we treat the plasmasphere. What is new is we take this the density from the plasmasphere model as a separate fluid and solve that in the MHD.
So in order to get the effect, you had to take the plasmasphere, make it a separate fluid, and treat it separately from the ring current. Then it could come out and form a plume and do all these things.
Yes, correct.
Okay. Thank you.
Okay, thank you. And the last question I'm seeing here in the chat is from John Haytusek. Do you want to ask your question? Since we are all asking. Or I can read that.
Sure. So I was wondering if you could elaborate on the differences between the grids in CIMI versus RAM. You said that CIMI uses an ionospheric grid and RAM uses an equatorial spatial grid.
Yes.
And it was my understanding that these types of model, that both of those models had used a grid where each field line each grid point represents a magnetic field line. And perhaps that understanding wasn't correct, but if it is, then the field line would be connecting both the equator and the ionosphere. And so it wasn't clear to me how the grids would differ depending on whether you thought of it as equatorial or ionospheric.
Yeah, you're right. I think along the field line, this depends on how you define a field line or a flux strip. CIMI and RCM, they define the flux strip by their ionospheric foot point. And RAM, I believe, for certain, the early version of RAM, they define the flux strip or field line by the equatorial crossing point. I think this is only bookkeeping thing, how you identify a field line.
Okay, thank you. So it might affect the spacing that you end up with in the grid, or how the details of the implementation details.
Yes, yeah.
Okay.
Because the like RAM is define the equatorial grid, so they have maybe in the radial distance they have equal or uniform spacing, but RCM and CIMI the grid in the ionosphere, so we cannot use uniform latitude grid because they will map to I don't know, when you map to the ionosphere, a map to the equator will be very weird. I think if you, I have a paper presented in just last year talking about how we set up the grid in the latitude in the ionosphere to make sure the mapping at the equator will be relatively uniform. Yeah.
Okay, thank you.
Okay.
Okay, thank you. Anybody else? We have a comment from Judy. Hi, Judy. Very impressive work, Mei-ching. Thanks for the comprehensive overview. And also, yeah, I also would like to thanks everyone. Thank you for attend our seminar. Thanks, Mei-ching. I hope see you in 2 weeks from now. Have a nice week and stay safe. Thank you.
Thank you.
Thank you. Bye-bye.
Nice talk,
Bye.
Mei-ching.